by Jesus Science. Hello. So, this is the introduction. The purpose of this lab is to demonstrate the first law of thermodynamics. The first law of thermodynamics states that change in energy equals work when there is no energy exchanged. In this lab, we use the spring force and gravity force, as those are the forces present in the system. Noteworthy formulas include the velocity update formula, the position update formula, the kinetic energy formula, and the potential energy formula. The procedure of this lab is as follows. First, insert a video into Tracker, per usual, collect the data in Tracker, and insert it into Excel or Sheets, and then export it as a CSV file. Once you do that, you can use it to create a model in GlowScript, and then find the graphs of the data sets. So here we have the Tracker graphs in the X component and the Y component. Now let's actually take a look at the Tracker video, and we'll be able to see the oscillations. So here we have the object oscillating, and of course the spring oscillating, and we can see that that I tracked the point mass of it at each point in the oscillation. So that's pretty interesting. But now, and now we have the graphs right here at the top right. So we have the X component right there. We can change it to the Y if we want to, and then we have all the data right here in this table here in the bottom right. And let's actually go back here to the presentation, the main presentation, and let's talk about the spring constant now. So the spring constant is found using the period formula, actually a derivation of the period formula. So in the period formula is as follows: T equals 2 pi times the square root of m divided by k, mass divided by the spring constant. So we know that time equals 1.77 seconds, and we know that the amount of time divided by the amount of oscillations in that interval, that's what time is, right? And we know that the mass is equal to 0.402 kilograms. So if we plug in all of our numbers, we find the unknown k is equal to 5.07. So let's now take a look at our GlowScript code. So show you the main things to keep in mind here that we changed. That's the mass of the ball. Obviously, you want to put 0.402. Let's see, gravity 9.8. The spring constant right here. So you want to put in your spring constant that you solved for. In this case, it's 5.07. And then you're going to want to change some of these vector formulas around too, right here. And something really important right here. These are these formulas that I mentioned earlier. So the kinetic energy formulas, the potential energy, the change in potential energy, the change in kinetic energy, and then the energy formula and the change in energy formula. And let's now take a look at what this looks like when we run the program. And here we're going to insert our CSV file, right? So CSV. And now we're going to use that one right there. And now it's going to start running, right? And take a look at these graphs right here, right? So we have position versus time, and we have change in energy versus time. And if you notice here, the energy is always constant, right? And this is very important. and just notice that the energy is constant throughout. It's a straight line. And here we have the system itself. If we zoom in a little bit, right? It is a little bit scuffed for some reason, but the important thing to keep in mind is that the energy is constant throughout the system. Let's go back to our main presentation and take a look at this. So, is the energy principle satisfied? The energy principle states that the total energy in a system will remain constant because energy cannot be created or destroyed. Yes. Very similar to the law of conservation of energy. In fact, a better way to state the energy principle is that energy cannot exit a system, right? But in this experiment, that principle is satisfied as seen on the energy graph in the previous slides, right? So it shows that the energy is a straight line in that graph, which means that it's constant, it doesn't change. So the principle is satisfied. So now let's talk about the oscillations. So you have the oscillations in the X component and the Y component. So in the period of X, it's 1.77 seconds, and the main component of that is the length of the object, right? And then in the period of y, it's 1.49 seconds, and this is due to the stiffness and the mass of the component, right? So what can we conclude here? We can conclude that the different periods are due to the differing makeups, different components of each x and y component, right? For x, it's being the length. For y, it's the stiffness and mass. All right, that is going to be all. Thank you for watching.
Thanks, guys.